Okay, everyone, I think we're back now, 9:40. I'll hand it off to Steve to lead us over the sustain portion.
I'm actually going to hand it over to Ryan. Ryan's going to get into the BMP model.
Can you mute yourself? Thank you.
Hey, Steve, can you hear me okay?
We can hear you.
Okay, great. Sorry, my headphones just turned off, but they're back online. Okay, so we just went through a lot of LSPC. So John and Steve went through the LSP model itself, the calibration validation process, and now we're going to turn a corner to the sustained BMP model. And so just like LSPC, we have a number of enhancements that were made to the model. And so one of them is a computational efficiency improvement. So just like LSPC, we migrated from a 32-bit to 64-bit system. So this just helps runtime. So this model runs faster than it used to. And the other three listed here have to do with BMP representation. So one of those improvements was under drain effluent concentration. So there are several options for modeling water quality improvement in the BMPs and sustain. Now we've added an additional option to simulate a maximum reducible effluent concentration. So if you've ever looked at data sets from international BMP database, those are provided in concentrations. And so now those data sets can be brought into sustain and integrated to represent that level of water quality improvement. Another improvement here is the BMP effluent discharge rate. And so low flow diversions are a type of BMP that don't exfiltrate water through the subsurface at an infiltration rate, at an inches per hour rate. Instead, it typically uses a CFS rate. And so instead of modeling just in inches per hour through the subsurface, now there's an additional option to pick an actual CFS discharge rate. And so you can pick 1 CFS, 5 CFS, whatever the rate is that a user is interested in simulating. There's that option to pick that flow rate now in addition to the already existing inches per hour losses through the bottom. And then lastly is an update to the bypass fraction calculation. This is a little weedy, but this is how the model at every time step is looking holistically at the available volume in each time step. And so now we've updated this so it matches a little bit more of what's likely happening on the ground with any of these BMPs. And so there's been an update there. And so what we touched on earlier is that sustain is a dynamic simulation of BMP processes. And these processes can be tuned or adjusted to represent different BMPs. So on the right-hand side is an example of what might be a media filter or a sand filter. And this can be represented in sustain, or we can also turn on some other parameters like vegetation index and underdrain to simulate a bioretention cell. And so the idea with this slide is that we have a number of essentially modular unit assembly processes that we can add and subtract from the model to simulate different BMP types. And so with this modular process, what we did is we developed a set of BMPs in our menu of BMP options. And so we have a number of distributed and regional BMP options. On the right-hand side is an example of a bioretention or biofiltration unit with a number of default BMP parameters. And these BMP parameters were garnered from predominantly local sources. We have all those sources listed here and in our phase 2 report that's going to be published next week. And then we also have, well, before I move on, the other point to be made here is that all of these are adjustable default parameters. So if a user wants to get into the sustain model as we've set it up on the WMMS model platform, which we'll be demoing later in the presentation, if they want to adjust the depth of 36 inches to 24 inches or 12 inches or any combination of these parameters and these values in between, they can choose their own design criteria and have it fit their project at hand. And so this is an example of one BMP. We also have another of performance parameters for each BMP. So this is still bioretention, biofiltration unit. And we have some effluent concentrations. These are from the international BMP database. This is how performance, an option for how performance can be modeled through the underdrain through the subsurface of the BMP. And then there's also options to set the optimization variable here, which is length. And so again, we'll get into this later in the presentation, but these BMPs can be optimized to fit or to meet the water quality criteria designated by a user. And so that's an example of one of these BMPs. We have essentially a list of these criteria and sources and default parameters for every BMP in this list. But there are likely going to be other BMPs that aren't captured in this sort of broad brushstrokes list. And so if there's a proprietary filtration unit or a proprietary unit or something that we haven't thought of that's not on here, we also have a default kind of open-ended treatment unit that the user can use to define essentially anything that Sustain can model or any set of variables that can be adjusted. They can be adjusted through this treatment unit to represent the model that a user is looking to simulate. Okay, so those are the default BMP performance parameters and design criteria. Each of these BMPs has an associated cost. Here's an example of bioretention and porous pavement. We have a box and whisker plot on the left-hand side showing kind of the range of costs associated with these. There's quite a range on some of these BMPs. A list of example of a few of the sources that we actually used to build this range of costs. And then on the right-hand side is a conceptual image of these two BMPs. And so the reason why this is important is because when we run an optimization or when a user runs an optimization on the optimization framework platform, they're going to be using cost to distinguish, what are the trade-offs in cost and performance and capacity between each of these BMP types. And so not all of these BMPs are treated the same in terms of performance. They all have their own design criteria and they all have their own costs. And so all these are put together inside the optimization framework. And so there's a lot more detail going into how that actually happens in action later in the presentation. This is just setting the stage. Similar to the BMP menu parameters and design criteria, the costs are also can be defined by the user. And so if there are costs that a user would prefer to use, this is a kind of an example snippet from our phase 2 report with some sources. These are those default values, some of those default values. And so again, a user can choose to use these. This is what kind of the default starter numbers are that we have made available. And so with that, I'm going to hand it off to Dustin. He's getting into the optimization framework details.
All right. Hi, everybody. Let's see. So I'm going to take the screen. Let's see here. Sweet. All right. Are we good? Thank you. All right. Hi, everybody. 126 people out there. It's so funny just kind of speaking into an echo chamber, but one day we'll all be in a room together again and it will be glorious. So I'm going to talk about we're getting closer to kind of the RAA and the optimization component where we're using WMMS to create implementation strategy. So first, I have a few slides to give some background and begin to make these connections to RAAs. I'm sure a fair number of the people that are on the webinar are interested in using WMMS for RAAs or know that WMMS was part of their RAAs. So let's talk about that just a bit. So EWMPs and RAAs in LA County. So really the EWMPs and WMPs, now they're just WMPs. We can just say that makes our life easier. Really marked a sea change in terms of planning in LA County for the first time as a community. LA County was able to digest the BMPs and the costs that would be needed to meet all the requirements in the MS4 permit, the billions of dollars to meet a range of pollutants from zinc and bacteria and toxics and nutrients and all of the usual suspects. WMMS 1 was used for a majority of the RAAs in the EWMPs, and during the EWMP development, there were a number of methods, assumptions, approaches, and a modeling workflow that was developed to create the RAAs. And this optimization framework that has been developed under WMMS 2 is really a way to make that workflow available to a broader community, and particularly on the data management side. So we'll talk a little bit more about that. But just a couple reminders. Here's an example from the Upper San Gabriel River EWIMP. When we're building an RAA, we're building an EWIMP implementation strategy. One of the early steps is to tell Sustain, to tell WMMS where the BMPs could be. Where could the green streets be? Where could the regional BMPs be? How big could those BMPs be? What are their footprints? What do their profiles look like? And so everything that Ryan was just going through was a lot of like the profile of the BMPs, and the screening becomes where could we put the BMPs, whether those are fixed or optimized. And so that'll still be a big part of using WMMS. And of course, WMMS doesn't, you can't go to the website and get this information for a group. This is where the EWIMP groups would come together and create these strategies and these options in this menu of BMPs, leveraging what's available from WMMS 2. Some of you might remember these curves from the original RAAs, and a really important thing to understand about Sustain is that Sustain does not just create, we don't just say we need a 42% reduction, what should the BMPs be? Instead, Sustain, through its optimization, it solves the strategy for a big range of reductions. So that's the x-axis on this curve. This is a range of strategies that would achieve from a 10% reduction to a 94% reduction. So from the original workflow, we use the cost optimization in the RAAs to identify a range of solutions, and somewhere on that curve is the target reduction that watershed needs. Okay, so if the bars, these curves, remember on these curves, the bars are the capacity of the BMPs. That's the left axis, and then the right axis is the cost. That's the red line. And so from this example from Arroyo Seco, the target reduction was a 39% reduction, and Sustain had created that the solution to get there was available from WMMS. And so that we call that a slice. That slice can be extracted. See the 39% reduction in the bottom of this table, and that is where some of you remember the recipes for compliance out of the RAAs. That's what that slice contains. It contains all of the detail for an individual solution. Okay, so remember, in most of the EWIMPs, in your appendices, there's these details of the amount of BMP in each sub-watershed to meet the pollutant load reduction targets that are in the EWIMP. And so what the optimization framework in WMMS 2 does is it really just helps users go through this workflow and create these strategies. And so yeah, that was when those strategies are rolled up for every single sub-watershed, then you get strategies that are by jurisdiction and by watershed. So a couple things we say optimization, just a couple things to kind of remind or help people understand what's going on in the background. What Sustain is doing, what WMMS 2 is doing when we when it receives these what are called BMP opportunities, Sustain is using optimization and it's changing the available sizes of those BMPs based on what you have defined as a user. So you said, you know, I could potentially have this much Green Street and this much regional BMP and this much LID. And then Sustain is going through a bunch, you know, thousands or millions of options to figure out what would be the most cost-effective way to get there. And those are the orange dots, really. So every one of those dots is a potential strategy, and the orange dots are the ones that are the most cost-effective. That's what's going on in the optimizer, as we call it, or the optimization engine. You could just fix all of the BMPs and not use the optimizer. That is an option when you're using WMMS, would be to evaluate a very defined strategy. Within WMMS and within the original RAAs, there's really two tiers, okay? Each sub-watershed gets a curve like the one that we just showed. And then at the watershed scale or at the jurisdiction scale, the optimization will help you figure out where to focus. Where should we put considering all of those optimization outcomes, where should the BMPs be put within the watershed or within a jurisdiction? That's the tier 2 part of the optimization, where you're searching all of those curves for each individual sub-watershed. So as you can imagine, the amount of data management within there, if you think about this curve, there's a time series associated with every single one of those dots. And so the management of the data and the time series has always been the biggest challenge with using Sustain at the watershed scale. And in many ways, the optimization framework in WMMS 2 is helping users do that, follow that workflow, and kind of manage those input and output files in order to get an optimization curve. So this is cool. I'm going to pan over and go to the WMMS webpage. Okay, and within the webpage, you see this tab that's called Utilities, and the utilities really help the user follow that workflow from formulating the problem to getting an implementation plan. And the problem formulation, there's no utilities for that part. That is really when you're setting up the simulation and figuring out what is it that we're optimizing for. Is it zinc? Is it bacteria? What is our critical condition? Is that a 90th percentile storm or an average year or some other option? So that's a very important part of the RAA, the limiting pollutant analysis. All of that good stuff is here, which would need to be decided on the front end. But once that is established, then the utilities help the users get through these steps to get an optimization curve. So these are the utilities here. There's 5 utilities. And within each one of them, I'm just going to kind of click around a little bit. Within each utility, there is a page where you can use the utility, an overview of what the utility does, some instructions on how to use the utility, and then there's always a user document. And these user documents are extensive. I mean, these utilities are extensive. And so, you know, within ramps, for example, there's the ranch utility, which helps bring existing BMPs into the workflow. There's a pretty extensive user document here to help understand what how to use that utility. And so that's really kind of the overall workflow where the user is pulling templates down, filling them out, putting them back into the utility, running the utility, and then getting an output that helps oops, sorry, that helps get through the workflow all the way up to the optimization curve. So again, each one of these utilities kind of has a page, tells you how to use it, has some templates, has a user document, all of that good stuff. To where at the end, the aha moment is when we get to the optimization viewer, so that now the users can create these optimization curves. And so the optimization viewer is really where the output of the utilities ends up being what we call a CRZ. And here's an example that Ryan is going to go through. The demo is really kind of walking through how one could end up with an optimization curve like this. And so now in a web-based framework, the user can create a curve, understand the different slices of the curve. I'm clicking on the screen. There would be a 50% reduction for the area that was studied. That 50% reduction would require $50 million in cost, this many acre-foot of BMPs, and the breakdown of what is in that slice in terms of the BMPs. And then also, with one click of a button, be able to get the output that is that recipe for compliance that I showed you earlier in an Excel format. So here's one recipe for each of the Jura sheds that were in that example pilot area, and the total capacity or the total cost based on what was entered in to the BMP assumptions, the design details, which are available still available in the output. The output's kind of reminding you what you put in there, and it's even giving you a nice graph for your report. So that's an overview of the utilities and how we've taken that original workflow and helped shepherd users through using WMMS to get optimization curves. And what Ryan will go through is a demo using that data that created that curve that we just showed. Before we do that, we're going to take a left turn real quick. Okay, so I've already said the word ramps, and ramps is a system that many of the jurisdictions are using for annual reporting and for BMP tracking. The ramps utility here is where you're able to bring the existing BMPs that are already in the watershed into the strategy so that you get credit. You get the reductions for those BMPs that are already in place. And in terms of the left turn is about the release that the flood control district, we kind of piggybacked on this webinar to show people this new released web page and web system that is available, that's been created by the Los Angeles County Flood Control District now, that we call the LA County Stormwater Capture Dashboard. Okay, so ramps is used annually by somewhere between 50 and 60 of the jurisdictions in LA County. But it's always been behind a login, and ramps is still behind a login. You have to log in order to get the information that's in here, manage the information, and etc. And there's requests in the past of, well, wait, how do I see that data, or how do we kind of use that data? And so the LA County Stormwater Capture Dashboard is a system that's now available at this URL that broadcasts the BMP locations. It gives information on individual BMPs. So I clicked on an LID project here, and there's different you get details for any project that you click on, including the capture, the estimated capture that is accomplished by that project. And right now, if you go to the URL, what you are seeing are the projects that are in ramps for unincorporated county. So by default, I'm sure someone's already like worried out there, like, are you going to broadcast my data without asking me? The answer is no. But we hope that over time, municipalities will add their projects to this dashboard, because it could provide a really important tool for the region, where we not only track rainfall, but we also can estimate capture, and capture on a real-time basis. So the capture dashboard is really a leap in terms of how we're using WMMS, because we're using WMMS on a real-time basis in the back end. And every time it rains, under this analytics page, the dashboard is tracking the rainfall. In this case, here's the year to date. So you can go to this page. Here's the year to date rainfall. You can see the rain on this pane here. You can search across different rain gauges if you want. And on a real-time basis, WMMS is being used to estimate the corresponding capture from LID Green Streets and Regional BMPs. And so that's this graph here. And so right now, all that's being shown is unincorporated county and the flood control district. But as a jurisdiction, if you went into ramps and you made your data available, you would be able to query and see your jurisdiction's BMP capture and performance. So how would you do that? Well, under ramps, so I'm now going out under ramps, logged in to ramps as unincorporated county, there is a little box here for all the projects. And for all of you right now, the default is to exclude the data from the dashboard. But you could undo that check mark, and then your data would be pushed to the dashboard in a real-time manner. It would literally show up on the map, and from that point forward, the capture would be tracked for that project and estimated. You can also get there. Some of you know the bulk upload form for ramps. You can also put that yes or no in that bulk upload form, and you can make your data available and be able to track the capture in your jurisdiction. But even if you're not part of a jurisdiction, I think, please begin to use this page. We love it. It's fun. When it rains, you just go to this page, and about 12 to 24 hours after it rains, you'll get updated capture estimates. And it really gives a sense of not just rainfall, but also the capture, which is really important for the region to begin to get a handle on what the benefits of these projects are from a stormwater capture standpoint. Cool. That was fun. That was a fun left turn. PJ, did I miss anything?
Left turn, yeah, can I add to the left turn?
Yes.
So the county and the flood control district, I get questions all the time. They know we have ramps. They know we have all the projects in the database. And they ask me, well, how much did they capture last weekend? And I get this question a lot because we want to convey this message to the public. We have a poster downstairs in our elevator hall that's constantly being replaced with this sticker that shows how much we captured. And we thought, because of this request that we get all the time, it would be better if it was automated. It would be better if it was real time. And that's what really led to the development of the dashboard. And so we wanted to show people, how are we calculating all these numbers? where are all the projects? And so all our ramps projects are on this dashboard page for the unincorporated county and the flood control district. And we're doing that as the regional leader, and we're doing that to show as example that, displaying this data to the public is a good way to gain trust and also show the public where all the projects are. Because if you see all the dots on this map, there's so many projects that people don't know about. And so we want to educate them as well. So this is part of our tool to educate, to inform the public about stormwater capture. I am hopeful that other municipalities and cities will also turn on their projects in ramps and show it on the dashboard as well. It's just a switch, like Dustin said, you could turn on and off. And then as a group, collectively, as a LA region, we can really show them how much we're doing, how many projects there are in the ground. I think it would be really impressive to the regional board, to the public, to NGOs, to show them really how much we've actually done. But I understand there might be some hesitation, and even though the data is in the RAMPS database, we will not show it unless you guys activate it. But I want to encourage all the cities to show their data, to make it transparent, just to gain more trust and to educate the public. This is an awesome website to show how many projects have been done. And so if you have any questions, I'm going to keep pestering all the cities to show them. It's going to be a great tool to show the public, and I hope you would turn on your data on the dashboard.
Cool. All right. So Ryan, we're going deeper, right? So we're going deep now on the demo side, right?
Yep, that is what's next. So I went ahead and grabbed control. So let me know if that's coming through. Okay, great. Okay, so one of the things Dustin was showing was the optimization framework. He was giving a bit of a tour on the WMMS model web platform, this framework and how it works in the utilities and the description, the support. And so what I'm going to do is I'm actually going to pause for a little bit and take a detailed step through each of these utilities, starting with before the utilities problem formulation. I'm going to work through each one of these until we get to the implementation planning bubble. And so the idea is that to show how the process works, the mechanics of this optimization framework, and also the resources and materials that users have available to them all along the way. Because I've got about maybe 60 minutes or so to get through this, and just a little bit of expectation setting up front. We don't expect any user or anyone in this presentation to understand all the details associated with the framework, how every utility is used. And I'm going to go through it all. I'm going to go through as many details as I can in that 60 minutes. It's going to be a little balanced because we only have about 60 minutes. But like Justin was showing earlier, we do have all those resources and documents available for users. So with that, I'm going to start with the problem formulation aspects of the demonstration, where we're going to look at kind of the what, the when, and the where. And that's, we're going to choose the representative water year, which is water year 2010, and a tributary in Upper Los Angeles River, and we're going to assess total zinc. And so on the right-hand side is a small case study that we chose for this demonstration, where we've got a dozen or so jurissheds picked out. And at this point, in using the optimization framework, a user would need to come to this framework with a set of BMP types that they've picked out, that they are interested in implementing in a particular model domain. And then they would have need to identify the footprints, potential footprints for each of these opportunities, and then the upstream drainages for each one of these across the jurissheds. And so that's sort of the starting place for where a user comes into this framework. And so here's that framework again. And I'm going to drop out of presentation mode. We're going to go to live demo mode now, starting with the ramps utility. So let me get that out of there. And I'm going to jump to our WMMS2 model platform. So Dustin did some clicking around. I'm not going to do any of that just yet. I'm going to keep it on the utilities optimization framework page because that's sort of where this whole process lives. And so in this demonstration, I'm going to be a presumed user of ramps, and I've got, I'm a jurisdiction, and I've got a number of existing BMPs that I want to integrate into my BMP optimization process. So like Dustin was showing earlier, a lot of kind of user description up front to explain what this is, how it works, and then additional detail in these user documents that are downloadable on the page to give a deeper dive on the mechanics, how to access the data, kind of the buttons you would use, the downloadables you expect. It also includes a lot of the assumptions that are made, because the way that BMPs are simulated in, the way that our BMPs are simulated in ramps is not necessarily the same way that they're simulated on a desktop in Sustain. And so there's a bit of a crosswalk that takes place here. So all those details are in the user document. I'm going to jump back out of that. And then I'm going to take a spreadsheet that I've already developed from ramps, and I'm going to upload it to the utility. So this is, what I did on Friday was I went to ramps, I did a bulk download, queried the BMPs that I was interested in simulating. I download those directly from ramps, and I upload them right to the utility. So it's really just one button here on this one. And so this is going to take a few minutes, or a few seconds rather, and we get from that is a spreadsheet, and it is a pretty detailed spreadsheet. There are 5 tabs, and it's going to include everything that Sustain needs to know about those BMPs, the simulation. It's going to be included in this spreadsheet. And so there, I'm going to go through each one of these one by one. The first tab, I'm going to zoom in a little bit so everyone can see a little bit better. The first tab is probably the friendliest tab. There are only 5 entries here. You pick your simulation date. We're going to do water year 2010, so I'm going to change this to 2009, ending in September 2010. We've got zinc as our factor here. This is the number of iterations per jurished. So I have a nice picture I can share. Dustin showed a version of it earlier. And so what this entry box here is asking is, when we simulate all of these BMPs and every varying configuration of them to find a cloud of solutions, when does the model stop? How many does it need to run before we say, hey, we have enough solutions now? And so this number changes based on, I'm going to hide this a little bit more. This number changes based on how many BMPs are going to be simulated. If you have 2 or 3 BMPs, you can probably use 5 or 10,000 iterations here and keep it pretty simple. If you have dozens and dozens of BMPs, you're going to want to use a much bigger numbers, at least 20,000, maybe upwards of 50,000 to really build out a full curve. And so I'm going to show what that cloud of solutions looked like, that curve. And so, like Dustin was saying earlier, each one of these little dots is a unique configuration of BMPs that Sustain assessed performance and cost for. And so you can see that a lot of these configurations are not particularly good options that you wouldn't necessarily want to implement. But there are these really, really good solutions kind of along this curve, and those are your best solutions. And so that's what this next tab actually looks at, is when we look at that whole curve, how many solutions should I be picking out? So I've got another image here that should illustrate that pretty well. So this is that same curve, but now we've picked out 100 inclusive best solutions from it, or 100 solutions from it. And so what this entry up here is saying, of that 15,000, how many of the best inclusive solutions should I pick out? And in general, we recommend, or what we do in our default is 100. That's 100 for the default WMMS operation as well. If someone was really interested in bringing down runtime, you could potentially go as low as 20. But in general, you're probably best off doing 100. That gives you a pretty full set of best solutions. Okay, so this is the first tab in setting up when is my simulation? What's the constituent and how many solutions should I be building? The next tab is going to be getting into the design details of each of these BMPs. And so what I showed before on the PowerPoint presentation was a set of infiltration wells, bioretention and biofiltration cells, and porous pavement. And there's actually some major BMPs or some multi-jurished regional BMPs in here as well. And so this next tab is pretty busy because it has all 120 possible LID types that can be simulated by the framework. And so there are 20 LIDs, 20 regional projects. We have what's called the TBD BMP, which we have more details about exactly what that BMP represents in the user documentation. So if you're curious about that, I'd recommend looking at that further. There are 50 what are called major or MJR BMPs. These are multi-jurished regional BMPs. These are regional projects whose drainage area encompass more than one jurished and can encompass dozens, if not more, jurishdicts. And so there's as many as 50 of these particular BMP types that can be simulated. These are the existing LID types. So this is in ramps. When I just did that bulk upload and download from the utility, it actually brought in these existing LIDs with it. And so now I've got a couple of BMP types that are actually characterized over here. So this is the list of all possible BMPs that someone can simulate. It's a lot of BMPs. One of the internal conversations that we had is how much detail do we let a user have? We want to give people as many BMPs as someone wants to model. We want them to be able to have that flexibility. But at the same time, we don't want this to be hundreds, if not thousands of rows long. And so we kept it at lengthy, but not too lengthy in terms of the quantity and types of BMPs. So it's about 120, 130 altogether down here. So that's going through the rows about each of the different BMP types that are available to be simulated. And then I'm going to start going through the columns from left to right so I can show each of the design criteria and performance parameter variables that were input into here. And again, these are all the default parameters. It comes pre-populated with those values. So the slides that I was showing prior with that sort of baseball card with bioretention, biofiltration, and all those values for those design criteria, performance parameters, those are all plopped in here for every BMP ready to go. So if a user is comfortable with those parameters, those values up front, they can plug and play. If someone has additional details that they would like to bring in here, this is the place that they're able to do that. If you want to change your media infiltration from 5 inches per hour to 3, that's where this is done. So I'm going to zoom in a little further. It's probably not easy to see via screen share. So these first handful of columns are just kind of nomenclature, and this is tracking for us to figure out the BMP type and the ID. The first 3 columns should be left as is. And so this is what Sustain needs to kind of track all these BMPs. But these next 2 descriptions can be used or can be modified by user if they want to change the name of a bioretention cell. For example, if you're doing a particular type and you want to say this is on Crenshaw, you can add that level of detail there. And if this is a set of BMPs along a particular roadway, now you can kind of capture that in this spreadsheet. So I'm going to keep moving along. I'm actually going to freeze the pane so we can keep this left-hand side kind of visible as we move across. The next set of design criteria is a lot about the physical layers of the BMP. So if there's a diversion rate associated with it, which is common for regional BMPs, at what flow rate is that diversion rate happening at? If the height of the BMP is the weir height, the ponding space, that's indicated in feet. The soil depth also indicated in feet. Porosity with the associated soil media layer, the infiltration rate of that soil media layer. And a lot of this information is actually captured in these notes to the user. And so I'm sure a lot of what is being gone through in my demonstration won't be retained 100% by everybody, but there's kind of a snapshot of each of these things encased in each one of these notes. And so there's a little bit of a high level snapshot up top here. there's actually a more detailed dive on it on the user documentation. So there's two places that a user can follow up if any of these, if you're looking for more information on what these represent, what these mean in the model into a BMP. So I'm going to keep moving to the right. There's a couple of underdrain and release type options where if you would like to simulate an underdrain, you can do it with a concentration-based effluent, or you can use it as a percent reduction benefit. And so that's actually done in these boxes over here, where let's say in this particular BMP, I want to simulate a 90% reduction of TSS in the underdrain. That's what I would do here, because this is the associated treatment for the first pollutant, which is total suspended solids, and then I've selected percent underdrain removal here. Again, that's probably maybe too detailed for our purposes here, but there is a user documentation that's going to kind of move or help a user be guided through this whole process. So I'm going to keep moving to the right. We don't have too many more columns, I promise. Here we're at the end now. Actually, before I get to the end, I'm going to spend a little bit more time on the treatment option. So the underdrain before, there's 7 pollutants being modeled in sustain, and if users interested in using a concentration effluent reduction or percent reduction through the underdrain, this is where that's done. And so those EMC values, sorry, not EMC values, those effluent concentration values from the International BMP database, these are actually those values that we're using here to represent performance through the underdrain for bioretention. And so if those numbers get updated through the years, which they will be, they can be updated here by a user themselves, and they can key that in. And the units associated with each of these boxes are also indicated on the header as well. So you can put in micrograms, milligrams, depending on the pollutant constituent being simulated. Okay, continuing right, pretty much getting close to the end. There is a column for outflow ID, and so there is no default routing network set up in these in this optimization framework, and that's because a user is going to come with their own preferences on how they want to route LID1 to LID3 to downstream regional 1 and 5 or any other combination of routing. And so that is left as a blank canvas for a user to come in and toggle however they choose that routing network. So if someone wants LID or the outflow from LID1 to go to LID2, they would just key in that ID in column B over into this column, and now outflow from LID1 is going to be routed to 2, and now that routing network is being developed in the optimization framework. BMP drainage area ratio, we have some additional support on that in the user document, so I would suggest people dig into that in the user documentation. The last set of columns is cost here. So we've got base cost, or kind of a standard cost, or a startup cost, or a fixed cost rather, for each of these BMPs. And all the costs contained for each of these are, again, the default values from the documentation, from the phase 2 report, and what we showed on the prior slides. So there's the constant cost, an area cost, which is a cost per square foot, dollars per cubic foot cost, and then a cost associated with the diversion rate, which is $1 per CFS rate. So again, these are all the default values. They come preloaded with a 20-year life cycle. And so we take the kind of capital costs up front, and then the annual operations and maintenance, multiply that value by 20 years, and that gives you that life cycle cost. If someone wants to do 30 years, 50 years, that's pretty easy to do. They can use the existing formula as it's set up here, or if they want to use something entirely different to develop area costs, this is a place where that's input. Okay, so that was a lot. This is probably the most detailed and involved tab that we're going to be going through. So if that seemed overwhelming, that's normal. It's going to get a little more, I think, easier as we go through the next ones. So what I downloaded before was the output from the ramps utility, and what the ramps utility did was it took that that BMP, those BMPs in there, and it lumped them into the BMPs as we see them over here. So we're not using all these BMPs, or none of these BMPs are coming from ramps, and so they're left as blanks. But the ones that are coming as ramps are automatically characterized as they've been set up. And so we've got 2 LID types. I'll zoom in here a little bit more, so it's a little more legible. 11,000 square feet for this particular BMP type, and then 6,000 square feet for this BMP type. And so this is the BMP size tab. This is where the maximum BMP footprints are entered in by a user. And I've got another spreadsheet that actually shows a little more detail on this. So I'm gonna leave that there for now and go to the drainage area. So again, what the ramps utility is doing is it's putting that footprint in the ground in a particular jurished, and then it's characterizing that upstream drainage area in terms of what HRUs, what hydrologic response units, that land surface signature from each HRU is coming to that downstream LID. And so again, there's not any of these other LIDs or regional BMPs in here yet. They can be entered by user, but the ramps utility has filled this out for these particular BMPs in this particular jurished. And so that's sort of the starting place for a user when they have a ramps bulk download that they want to characterize BMPs to get it into this optimization framework. This is the first step. This is what that first step looks like. I'm going to close this because I've got a version that I've tailored for our model domain area that we picked out. So I'm going to bring it over here on our main screen. And again, this is still the same spreadsheet template, but it's been adjusted to fit exactly the design considerations and constraints for that upper watershed area that I was showing before. So what we were looking at before, this area, these 12 jurissheds, I've got a spreadsheet template set up to handle that here. And so I'm going to walk through this again just because it's probably good to have a little bit of repetition. And I've also scaled it down a little bit. So before we had 120 BMPs. In this simulation, in this demonstration, we're not doing 120 or 130. We're doing, we got less than 10 here. So to save myself sort of the mental energy of looking at all those every time I open this tab, I've skimmed it down to just what I need so I can kind of move through this a little easier. And I would recommend that to anyone who's going to be using this template. If you only have a handful of BMPs, pin it down to those BMPs so that you can kind of make it a little easier for yourself. So I reduced the number of rows, but the columns across here are still all the same. I still have the physical description of those BMPs, those default parameters being used. I still have the underdrain selection and then those associated percent pollutant removal or those effluent removal as indicated by the underdrain. And then those 20-year life cycle costs are all set in here as default. So I haven't really done much. I've done a little bit of routing change. So now I have one LID type going to LID 4, and then I've got these multi-jurished regional BMPs. 2 and 3 are being routed to 1. So I've set up a little bit of a routing network in here to connect everything, but that's all I've done to this front page so far. Okay, so I'm gonna go through these 2 tabs one more time. Because now I don't just have the existing LID from ramps, I have also my proposed BMPs. And so this would be the expectation of a user is that you start with your existing LID as characterized from the ramps utility. And then added to that is a characterization of those new additional proposed opportunities and their upstream drainage areas. So that's what's done here, and I've got a graphic here on the right-hand side to show what that looks like, a little bit about what the process and what's involved to do that. So it's just taking those areas, cookie cuttering them into the HRU raster, which is available, on the interface for this utility and bringing it into this format for the optimization framework. Okay, so I'm going to go through the size tab again to make sure that that's clear. I've made it a little cleaner, a little simpler, a little easier. Again, I've got these handful of BMP types that we're simulating. I've got the multi-jurished regionals, which are these larger regionals that drained multiple jurissheds. And I've got those existing LID from ramps. And so it's broken out by jurished, by LID type, and this is how the model, this is how the sustained optimization framework is expected to receive this information so it can get integrated into the process. The very last slide is the major BMP routing tab. And so those, we call them major BMPs just because it's shorter than multi-jurished regional BMPs, but the idea is that these are not just regional projects that exist within one jurished and whose drainage area is encapsulated by one jurished. They can actually extend to multiple jurissheds. And so they may have reach and coverage beyond the jurished that their footprint is within. And so to handle that, there's a process that's been developed to streamline that process where a user would input the percent coverage of each of these jurissheds, and that gets translated back to an HRU coverage. And so what the model will do with these percents is they're going to go back to that HRU raster and cookie cutter out 90% coverage for each of these jurissheds, and that's going to be the upstream drainage area to each of these BMPs. Okay, so that was a ton of information, and now that this has been completed, I filled out each one of these tabs. I've got all the information. I feel good. I feel ready. I'm ready to upload. At this point in the process, it's likely that a user has spent weeks, maybe months, getting all that information together. And so it's a tremendous amount of effort and resource involved to getting a user to that point. And then the utility is really going to take care of the rest of it. And so I'm going to go to the BMP opportunities utility, which is the next utility in the process. Again, we've got descriptions up front to describe how the utility works, what's it doing. There is the user document that will give an even better detailed description of what I just went through. So if any of that, long list of performance parameters or any of these details you need additional information for, this user document goes through all of that and can be accessed from the website. So I'm going to drop out of that. There's also a number of other resources available. The HRU raster that a user would have to use to characterize their drainage areas is available right on the page. The jurished layer that a user would have to use to kind of understand where their drainage areas are relative to the model domain, that's available. That's a GIS shapefile, and that could be used in ArcMap or a similar program. So we've got a number of resources here. And I'm going to take that spreadsheet that I just walked us all through, and I'm going to upload it. And so at this point, like I was saying, a lot of energy and excitement and resources have gone up to this point, and you upload it, you click process, and you get errors. So this is something that happens to us when we were developing this, but also using this for some of our tasks, is we would get errors about, oh, you didn't use the appropriate naming convention, or you adjusted a cell that the model wasn't expecting you to adjust, and that needs to be reverted back to the original. Or there's something happening in one tab in the BMP size tab, but it's not listed in the drainage area tab. So we've got a whole host of error messaging that should indicate to a user what's happening. This error for me indicates that I've got a mismatch in my regional BMP drainage area and footprint, meaning that my major BMP is in one, or my regional BMP is in one jurished, and my drainage area is in another. And so those actually need to be co-located so that we can, so the model can simulate that BMP. And so that's what this error is indicating. I'll open this user document one more time, because we do have a whole host of troubleshooting section that a user can go through for more context on some of these errors. Some of them are just a timeout error. So if you get a network error, that's probably an issue with the internet during the upload time. So just reload the page and try it again. A lot of these are more detailed. And a first-time user, I imagine, is going to be spending a bit of time getting familiar with this. So don't get frustrated if you get errors. It's part of the process. Seek out that troubleshooting section. It's going to be a big help. And then I'm going to reload the page. And I'm going to upload a fixed version of that spreadsheet that I was showing before. So I'm going to hit process again. What the utility is doing is taking that spreadsheet very quickly, and it's going to transform all that information that was in these cells, locked away in these cells, and it's going to put it in sustained input files. And so what may have taken, weeks and thousands or hundreds of clicks before to kind of move all of that data from tabular format to a spread or to a text file format is now done with one click in about 2 seconds. So I'm going to open this zipped folder up, and it's actually going to have a package of, I'm going to bring this over here. It's going to have a package of folders and files that a user is going to use to execute the optimization framework. So I'm going to pause here because this is kind of a big turning point. Up to this point, we have been dictating BMP performance parameters, design criteria. What do these BMPs look like? Where are they? What's upstream? What's the routing? How do they perform? All that information was encapsulated in that spreadsheet. And now we need to move that over to generating input files so we can hit go on the optimization and actually run and actually understand of all those BMPs and all those combinations, what is the performance associated with each one of those? And so that's what this folder structure is. It's a launching pad to run those BMPs in the optimization framework, the actual two-tier process. And so what a user would do is take these zipped files, they would copy, paste them over to the appropriate place on their C drive, and the appropriate place is indicated on the user documents again. So I've already kind of got this all set up, so we can move through this pretty quickly. This is a folder structure that a user would have to create on their environment, and then they would copy, paste, and plop the input files in folder structure that was provided by the utility. And again, if that's not especially clear, there is user documentation to kind of show that process in more detail. Okay, so now that we've got our input files, we've got our BMPs, we're ready to go, we're excited. I'm going to go into my optimized folder. This is the first tier of the optimization. So one thing I showed before was this big cloud of solutions. This is what we're going to generate. So every Jira shed gets its own cloud. This is probably the best looking cloud I've ever seen in terms of solutions being generated. The more BMPs you have, the more kind of nice the cloud looks. When you have less BMPs or kind of BMPs that their performance behaves kind of uniquely or I guess strangely, sometimes the clouds look funny and they can actually take like step functions, and that's normal. So not every cloud is going to be as nice as this cloud. In fact, most clouds probably won't be. So a little bit of expectation setting there. So I want to build a cloud for each one of those Jira sheds. I can, if I wanted to, I can look at those input files. I have them set up here as Excel spreadsheets, but they're actually text files. I'm going to open one up real quickly just so users can kind of take a peek at what's inside. This is for Jira Shed 700-549, and this shows all of those parameters and all of those design criteria that we were setting up in that spreadsheet. They got kind of placed into here at the appropriate locations. And so we've got our model time frame, where the output's going, the HRUs being assessed, the BMPs being considered in this particular run. I'm not going to dive too deep into that, but that's there. That's what Sustain. That's how it understands and integrates those parameters that we provided before. So I'm going to hit run. This is going to launch a batch file. This is going to do a number of different things. It's going to open up every one of those input files in order. It's going to run the HRU time series going downstream to each of those BMPs. and it's going to toggle between different configurations. And so what we did before is identify that we want to set up a cloud of 10,000 solutions, and now Sustain is kind of running 10,000 solutions, and it's using its genetic algorithm to progressively find a better and better and better solution. And so it's going to fill out that curve more and more and more. And so I ran this last week. It was 12 Jira sheds, as indicated by the batch file here. 12 Jira sheds at 10,000 runs. That took about 3 or 4 hours. So that gives you a sense of, if you have a small area to develop those Jira shed curves for each, it takes about 3, maybe 4 hours to do that. And that's just the first tier. And this is with a 1-year time series. And so a user could choose to do hundreds, and it's likely that there are going to be those who are going to want to do hundreds, if not more, Jira sheds at once in one particular run. They may want to do a longer time series, although that's not likely. 1 year is probably the maximum that most people are going to do, but that really is going to draw out the run times. And so it's important to understand upfront what you're getting into in terms of how long you should let your computer kind of set and rest. And sometimes it's a weekend and sometimes it's a week. So be prepared for that. So if 3 hours went by, that model would finish. We would have a cloud for each BMP, and they would be contained in each one of these folders. So in each Jira shed, we have a text file, and every solution that was run, we can open it up. It's going to give the performance of the BMP, the size associated with it, the cost. This is a little messy. Users don't need to go into this. I'm just kind of showing this for the sake of completeness. But that's what the batch file is doing. When it's running all those iterations, it's filling out this output file with each one of those results. And so the batch file actually zips up those results. And once that's contained, the user goes back to the optimization framework, and it goes next to the inclusive best solutions utility. So we just finished the BMP opportunity utility, and now we're in this optimization. So I'm going to click on inclusive best solutions. Again, description, documentation up front to give a little more detail about what's going on here, how the mechanics work. What I'm going to do is I'm going to upload directly the zip file that we just showed in that folder. Let's go to it. So I go to optimize, the folder I was just in. That's a zip package. I'm going to upload that there. I got a WMMS file. The WMMS file is sort of a metadata file. It's in the for viewer folder. It's not much that needs to be said about it, but it's something that needs to be tacked on with every utility. And so that's going to be in this sort of platform that I was describing earlier, contained within that first download from the BMP opportunities utility. So I'm going to double click on that. That's going to upload. I have the option to choose a target reduction by Jira shed. In general, it's always 100% reduction. We want maximum reduction. There may be instances where someone wants to dial that down for a particular reason. Unless there's a very specific reason for doing that, there's generally not any reason to do anything other than 100%. And so what this utility is going to do is take those clouds, one cloud for each Jira shed, and it's going to identify the inclusive best solutions from each. I showed both of these images before, but just to kind of bring it back to kind of mesh these two ideas that are happening, is we have the cloud, and we're not necessarily interested in these poor performers. We're interested in those very, very best solutions. That's what we want to take with us to the next tier of the optimization. And so this utility is going to do that. So I upload the cloud, upload my metadata file, press process. It's going to take maybe 5 seconds, maybe 10 seconds, shouldn't be too long. And then I get another zip file. You're going to be getting a lot of zip files as someone goes through this. So I'm going to open that up. And all it did was it took every Jira shed, every cloud that I gave to it, it gave me back that best solutions and then the time series and performance associated with each one, so that I can take that up to tier 2 optimization. So what a user does is copy paste these folders here, and we're going to go back to kind of our platform here. That's not it, that's downloads. We're going to go back to our platform here. which is on our C drive. We're going to go to the next folder, the tier 2 optimization folder. And I'm going to put the output I got from the utility that was just on the right-hand side here. I'm going to paste it here, and I've already got it pasted here in advance. And now the tier 2 utility is going to take those best solutions curve, and it's going to associate a performance with each one of those, a time series performance associated with each one of those. And that goes to the next step in the optimization framework. So what I'm going to do again, just like we did for the first tier of the optimization, we're going to execute this optimization with a batch file. And so I double click it. It's going to look at those input files. It's going to look at any associated time series. It's going to grab those 12 juror sheds, and it's going to start running each of those best solutions. And what it's doing now, instead of 10,000 solutions in the cloud, it's just running those 100 that we had before. So those orange dots, if those were inclusive best solutions, it would take those 100 and it would run them for a full time series, so we can get that performance so they can be evaluated downstream at the multi-juror shed regional BMP projects. This one runs a lot faster. This one is actually done in 30 minutes because we're not doing 10,000. We're only doing 100 for each. So it actually goes quite a bit faster. I'm gonna move it off to the side. After about 30 minutes go by, what a user gets output from that batch file is a zip file, which is going to have all the results from that kind of neatly contained. And so what Justin was mentioning earlier is that this optimization framework, as it existed for WMMS 1, as it existed for the RAAs, this was kind of, these time series, these batch files were sort of floating all over the place. And it was real challenging file management and folder management structure, because you often had multiple people over a long period of time figuring out what's going on and how we're bringing this all together. And we're oftentimes doing multiple iterations, so we have to keep all of the iteration management straight too. And so really what this does, it keeps everything really nice and really tidy. So the input files, all of them always contained in the input folder. Output from that batch file always contained in that output folder. And then at the end of a run, it's always wrapped up nice and neatly together. A user doesn't have to go and find them. The batch file will do it itself. And then this is, again, what just gets uploaded right to the utility again. So really, the optimization framework, as it exists on a user's desktop, is a file management structure that enables them to run the optimization, keep track of the input and output files easily, and then just bring on those output from each up to the utilities as they exist on the WMMS platform. So kind of a more detailed description there. So once I have done that, I'm going to go to the next step in the utility. So I run inclusive best solution. The next step is assessing multi-juror shed regional BMPs. So I'm going to click on that utility. These are handled differently because the BMPs are simulated at a juror shed scale, and so everything is kind of encapsulated in that juror shed. And when we have projects that exist outside of that scale, they have to be handled in a separate analysis so that we can also optimize them with the other LID and regional BMPs. And so there's this additional utilities that kind of meshes those two together and brings it together. And again, there's a description up front to describe how all this works, a user document that's going to go through in more detail than I'm providing here, how and why and what user does to prepare. But again, as far as uploads, it's really easy, it's really neat, it's really tidy. It's us taking the zip file that we were looking at in the to production folder that we just ran. It's labeled major BMP tier 2 package. So we're going to double click on that. That's going to be our upload. And then again, our meta file needs to come along for the ride. So I find that in the for viewer folder, bring that along with us. And then we're going to get another set of utility output that goes back to our kind of platform that we have here for the 2-tier optimization. So I'm going to click on that output. I'm going to show what that looks like. And really, this is just output from those best solutions curves from each of those juror sheds. And it's going to go to those major BMPs, because those major BMPs don't know necessarily what the runoff is going to it until we've set up this structure so they can get that information. So These files are one for each major BMP, multi-jurisdiction regional BMP as described in the utility document. Again, I'm going to copy paste that over to our kind of desktop platform that we have here, and that goes into the next folder. And again, I'll kind of harp on kind of the structure of this. The idea is that you start at the first folder, 1, optimize, and then move to 2, production, and then move to 3, major BMP production. So it's also not just kind of manages everything, but it's also sequential. So to hopefully kind of give a sense of direction to this whole process, because it is, I remember when we first started using this whole thing, I would get turned around pretty quickly about kind of the order of things that we were doing and how we were doing it. So it's ordered sequentially, and then also the documentation, again, goes into a lot more detail to guide someone through that process in the event that they do get turned around. So again, I am at kind of my input, output, batch folder structure. I've got my output from my multi-jurisdiction BMP utility I have here in the background. I've pasted it in here, and it's ready to run the next tier of the optimization. So again, I just double click a batch file. This executes the instructions for simulating the BMPs, the multi-jurisdiction regional BMPs, and then the upstream time series associated with them. And again, it's just showing 100 of the best solutions. So it's feeding that time series down into those multi-jurisdiction regional BMPs. So again, this doesn't take as long as the Cloud One simulation. This takes about a half hour. And so when a half hour has passed, a user is going to get, again, another nice, tidy, zipped up package. All the output that a user needs to assess the tier 2 and the major BMP optimization, that's contained here, and a user will just bring it with them to the next utility in the process. We're getting close to the end, 2-tiered optimization utility. And what this does, this brings everything together. It brings the upstream LIDs and regionals. It brings the multi-jurisdiction regional projects and their varying sizes. And then it brings all those options into one place so we can figure out what are the most optimal combinations of each of those BMPs. And if we were to implement a particular slice or a particular suite of projects at every % reduction along a curve, what are those BMP suites? So again, I'm going to go to our platform for optimization on the user's desktop. I'm going to go to the most recent zipped up package that we just developed from our last tier of the optimization. And that's this fella here. I'm going to upload that same WMMS file, metadata, and that's here. There's a toggle for process with major BMPs. And since there are multi-jurisdiction regional BMPs, we're going to toggle that to yes. And that helps the utility understand what to expect in the zip. And so now it knows to expect a couple different types of output files. And so that's a simple yes or no, and that helps the utility understand what's headed its way. The last thing is a scenario definition file, and we have a template for this. And I'm going to give a really brief overview of what it is here, because there's a lot of details associated with it. And then in about 2 minutes, John's going to give a little bit more of a more detailed approach to this. So in short, it sets up the assessment area that we're looking at. So I'm going to look at just one scenario where I have a single assessment point and I want to evaluate flow, and I want to do it across all 12 of my jurissheds. And so in essence, it's saying at the outlet of all 12 jurissheds, what is my performance reduction capabilities and capacities for the BMPs provided for average annual flow reduction. So that's what this is here. And I think we have kind of a lookup over here to indicate how users should use the kind of the name you can vector for this factor. So if someone, for example, was interested in also looking at zinc reduction, they would use this naming convention for zinc reduction, essentially just a copy paste of this guy over here into the factor. And now we can actually assess a couple of different, we can not only assess flow, but we can also simultaneously assess zinc load reduction in average annual reduction, so average pounds reduced per year. And so that's the scenario definition file and kind of a real quick snapshot. Again, John's going to go into detail in just a minute. I'm going to upload a version that I have handy for us. It's going to be this guy here. And that's actually the same template that I was just showing there. I'm going to hit process, and this button is kind of the culmination of this whole process. We want to assess those BMPs over this area for these constituents with this cloud of solutions. And then now all that possible evaluation has been kind of brought into a single CRZ file. So this is where I'm going to turn it over to John. He's going to give a little bit more of a detailed look at the scenario definition file, because there's a lot more that a user could get into in terms of do we want to do a basin-wide assessment? Do we want to just look at the hydrologic boundaries, or am I only interested in the jurissheds in the city of LA in a particular area, and I'm not interested in other cities in a particular assessment? So there's all sorts of sort of scenario play that can happen there, and it can be very easy and very basic, as I just showed in that sample. But there's also opportunity to make it a whole heck of a lot more complicated, which isn't necessarily always required. So, John, I think you're getting ready over there, and whenever you're ready, you can grab control and show us what you got.
All right. Thank you, Ryan. Wow, that was an intense amount of information. And so I think, I hope you're getting an appreciation of the level of information that's available. And like Ryan mentioned, this is really about streamlining the workflow and making it so that it's an aid to the modeler so that we can sequentially and logically trace through the sequence of operations. Now, just to step back one bit to look at what it is that we're doing here at this stage. Ryan mentioned jurissheds. He mentioned first tier 1 and tier 2 analysis. We gave an overview of this before. I'll just recap briefly before we go into the scenario definitions file, because I think it'll help to put things into context. So the two-tiered analysis that we're working with here, each of those curves, the clouds that were developed for each of the jurissheds, and when we say jurished, that's a combination of jurisdiction and hydrological boundaries. You know, water flows downhill. When you intersect it with jurisdictional boundaries, all that gives us is an accounting mechanism that we can then roll up our results by jurisdiction while maintaining the hydrologic connectivity of our system. So in this graph, each jurished is going to have a cost effectiveness curve that's derived from the cloud of solutions, and then the 100 best solutions are selected out of that. That's represented by the yellow dots on this curve. So I have n number of jurissheds that I'm simulating in my system. At tier 2, Sustain is going to, instead of going down to the BMP level and looking at each of the opportunities, at tier 2, we are selecting from among the optimized solutions in the tier 1 curves. So now our search space is a lot less. That's why Ryan's runs for the tier 2 take half an hour instead of 3 hours. It's a lot faster. What that gives us is then the ability to run different kinds of scenarios. And so the scenario definition file that we're going to look at in a little bit shows how you can take the core elements of these tier 1 building blocks and then reconstruct them in a different way to ask different questions at the tier 2 level. Because ultimately what we see on this curve on the right, that's the tier 2 curve. That's the one that Dustin showed from the EWIMPs, where you have that scatter of solutions, you have the stacks, and then you choose your slice. That tier 2 curve is selected based on all of these component tier 1s. We mentioned the word major BMPs, multi-jurished regional facilities. All the LIDs are happening within a subwatershed, but there are large facilities that drain multiple jurissheds. So in this schematic that you see here, A, B, and C, those represent 3 major BMPs in our network. And in our example, we also have 3 major BMPs, 2 of which are upstream of 1 downstream major BMP. And so There is an interplay there in terms of impacts of treated water upstream, reducing the need to treat additional water downstream. You see all those dynamics playing out. Sometimes because of the size and the composition and the construct of the major BMP, you can see the cost efficiencies, economies of scale baked in as you treat downstream. Other times you see it more effective when you treat upstream. The scenario definition file gives us a way to quickly construct different scenarios and look at what happens. Another really interesting question, which is going to be part of the RAs going forward. Multiple jurisdictions sometimes are contributing to these major VMPs. Water's flowing downhill, doesn't care where it originated or where it came from. All it knows is I'm at this location, like C, for example, is downstream of 2 jurisdictions. And so A treats one jurisdiction, C treats another jurisdiction. It's physically located in one jurisdiction downstream, but it's treating water that has come from upstream. So at some point, we're going to have to do some cost allocation, sharing of that cost across the contributing jurissheds. This is all part of the scenario definition file. All right, so that just gives a little context. We're going to open the file now. So I have a scenario definition file that here we go. We're going to set up 2 basin-wide scenarios. In this case, we're looking at scenarios 1 and 2. We're still dealing with the 12 jurissheds that Ryan had loaded up. We're going to say, let's say the first time we want to optimize for flow volume reduction. So in this case, we've set it up with the objective of a basin-wide evaluation. What you see the columns in here, column 1 tells us our scenario. All of the jurissheds that are part of every scenario have to be hydrologically connected. So in the schematic that we saw before, it would include all the jurissheds, all the subwatersheds that flow, regardless of what jurisdiction they belong to, hydrologically connected. We get to pick in the scenario definition file what factor we're optimizing for. And then this label here is an aid to us. It's telling us that we are looking at all of these jurissheds together, regardless of what jurisdiction they came from. Now, if I want to run a different scenario, let's say one that focuses on flow reduction versus zinc reduction, all I have to do is duplicate this set of subwater jurissheds and then change my target from flow to zinc. Now I've specified that I want to run optimization for 2 scenarios, one for flow and one for zinc. I could even get a little bit more sophisticated, and let's say I'm looking at one other scenario here. In this case, let's say I do want to look at jurisdictions, and I want to look at the difference between what if I optimized where all the jurissheds were participating together versus if each jurisdiction was required to hold their own in terms of the target reduction that they're trying to achieve. So in this case, I'll set up my scenarios a slightly different way. I'm using the same factor in this case. It's all for zinc reduction. I have the same number of jurissheds that are hydrologically connected. What the distinction here is, there are 5 of these jurissheds, which are part of the county, and then the remaining 7 are part of the city's jurisdiction. And so now what Sustain is going to do is it's still going to run the hydrologically connected, but the jurished now allows us to roll up our outputs, those same curves that we saw. We can have one curve for the county, one curve for the city, and then select different slices from those curves, and then compare those slices to what if I had optimized basin-wide. So that's what the scenario definition file does. There's one column in here which we see in here, it just says split. So the multi-jurisdictional regional facilities, for the purpose of the EWIMPs, we do want to show a shared responsibility approach. So split is essentially the default setting for here. So all of these are going to show split. All right, so once we have defined that file, then that becomes an input for the tier 2 runs that like Ryan was showing. And then from that comes an output file, which we had got a sneak peek of before. That's the CRZ. So that CRZ is going to be here. And I'm going to load up the output CRZ that we saw before. So this is a CRZ for the first scenario where we're optimizing basin-wide for flow reduction versus zinc reduction. And we saw this curve before. We're going to talk a little bit more about what is in here and what are we looking at. So the objective for scenario 1 was flow reduction, as we saw in our scenario definition file. The objective for scenario 2 was zinc load reduction. Now, this curve tells us that if I needed to achieve a 14% reduction, this slice, I can see the composition of the BMPs that were chosen here. In my network, I had BMPs, major BMPs 1, 2, and 3 that were part of that network. Remember, I can always go back to my opportunities and look at how I configured it in terms of LIDs within a jurished versus all of these majors. So the spreadsheet that Ryan was showing, here are my LIDs that exist within a jurished. I am looking at porous pavement that is upstream of LID4. In this case, LID4 is a bioretention basin. So I have a little bit of a treatment train in this example. Porous pavement, the overflow from the porous pavement will be treated by the bioretention downstream. And then the rest of these, LID opportunity 1 and 13, those are parallel to my treatment train of porous pavement and bioretention within a jurished. Now I have my jurished routing. This tells me that these 3 jurisheds and these additional jurisheds, we'll make them a slightly different color, are grouped together. These are the contributing jurisheds that flow to major 3. These are the ones that are tributary only to major 2. And if I go back to my original file, it tells me that majors 2 and 3 are both upstream of major 1. So in column X is where I have to define my routing, my connectivity of these major BMPs. Remember, these majors live in the spaces between the jurisheds. And so we have major 1 downstream of 2 and 3 in my larger jurished collection of 12. So that's what's happening. So when I look at the results, I can now interpret this and say, wow, okay, look, optimization preferred to utilize major 3 first. It was the most cost effective right out of the gate. On top of that, we see it chose to do major 2. These colors are a little close. If I want to change that color to something else, I can select a slightly different color to distinguish it a little better right off the interface. But here is major 2 coming in on top of the major 3. So right away, I get a notion that, well, it was a little bit more cost effective to manage those tributary areas before building the large regional facility at major 1, because major 1 didn't kick on until around the 20, almost 30% solution. I'm starting to see major 3. Now there's a big step here, because as soon as major 3 does kick on, my performance goes from about 25% to almost 45%. So suddenly you can really see the economies of scale associated with that one major downstream of both of those 2 minor majors. And you see the performance pick up there. So that's what we're seeing here. And then after it has built these major BMPs, based on this problem formulation, I'm reading from these results that it was really cost effective to do those large regional projects. And this is a really important piece of information for us as we go forward and we think about these RAAs. Sometimes these opportunities that are going to be cost effective are those that give us these economies of scale as pictured here. LID is also providing us some benefit, but the stacking order that you see these curves, this tells us what was cost effective because those get exhausted first. And then it started to dabble in a little bit of the LID, bioretention, and then on top of that, infiltration trench and LID, and then the bioretention on top of that. So you can see some of the dynamics of the results. All right, now let's say I want to take this solution, 45 solution, and generate my plan. We saw a view of this before. Dustin gave us a preview of this. So when I look in my implementation plan, we see the capacities and the costs. We see the design details. All of this is captured in there. And I have a graph as well. So all of this is there. If I want to choose a different slice, if I go back to the interface, I can press generate plan and it'll give me another spreadsheet for that slice. So I can generate as many of these as I like. The output from the optimization is not a single solution. It is this entire matrix, the CRC. That's why we have that terminology, capacity, reduction, cost. That is the answer that Sustain provides. And then we get to pick from that answer to inform our policy decisions. So let's say that this is the plan that I want to run. And now I want to take this solution, push it back through to get the time series, the runoff time series that comes out from Sustain, and then send that time series back to LSPC. Now that exercise would have taken a really long time and it would have been rather labor intensive. But now the utilities also provide a means for us to do that. And the way that it works, we take the solution of interest, and then we can click this button that says generate Sustain to LSPC batch file. If I click that button in a few seconds, it has gone to the spreadsheet configuration. It has built for me a series of files, and within that series of files is another folder structure that has the input files that I need to run Sustain and the configurations that are going to give me ultimately the time series that I can plug back into LSPC and then run the results. Now, what does that look like? I'm going to do one quick preview of that process. One more here just to put it into context. So when we have the pieces from our modeling system, LSPC provides for us the surface runoff boundary conditions to Sustain. That's on a unit area basis. Those become the boundary conditions that we take the opportunities for BMPs and we route that runoff into those BMPs. That generates for us an alternative set of runoff conditions at each jurished outlet. Now it's important that we preserve the mass balance. So when Ryan was setting up the configuration in the opportunity space, there was an important column that was untreated outflow. So Sustain gives you the chance to reconstruct what goes where in our spreadsheet, but the untreated outflow, that column is just as important because that's the one that's going to tell us that in each of these jurissheds, this amount of this HRU was not treated. And this amount was treated by LID1, this amount was treated by LID10, and so on. All that is happening and defined here in this workbook. So the untreated flow goes to the jurished outlet. We preserve our mass balance. And then at the end of that process of running the batch file, Sustain utility sequence is going to give us a series of linkage files. This was one of the other updates that we made to LSPC. the ability to easily connect to a linkage file that comes from another model with a specific format for it, sustain. And in this case, because that linkage file represents a treated runoff outflow through a network of BMPs, that is going to need to replace the baseline surface runoff that was simulated in the original model. So the top pathway here, kind of in the light blue shaded area, the model takes the unit area runoff by each jurished, plugs it in, routes it through our reach network with all these flags turned on. So it's allowing the normal simulated surface interflow and route flow to pass through the model. In the alternative series down here, after linking to sustain, we take the output from that series, we replace it with the linkage file, and then route it through. An important distinction is we have to turn off the surface runoff from baseline because we're replacing it with the new output from sustain, which is represented in card 435. So at the end, we can look at the stream comparisons of the attenuated versus the baseline runoff.
So, we're not going to go through that process because I think one of the finales, I think one of the things that people are primarily interested in is their implementation plan and the curves and the output that were typically used in the RA updates. But if folks are interested in knowing what the effects would be on receiving water quality, that utility is available. So just, we've got 40 minutes left, and I know that that was a lot. Now, I guess, you know, apologies. One thing I could say is welcome to modeling. Welcome to our world. We're bringing you into our world. And I think, you know, as complicated as it may have seemed going through the demonstration, I think hopefully folks have a healthy respect for how complicated it was before that workflow was managed through the use of these utilities in this new platform. So we're basically, the county is giving it away with where anyone can perform these processes and go through the workflow for the optimization. It does require some modeling expertise. I think, you know, there is an expectation that the user has some familiarity with LSPC and sustain and understands how to run those models before we go through this workflow. So I just wanted to make sure that part of it was clear. However, you know, there is a lot of user documentation. There's, again, I'm just to remind everyone, the main reports for WMMS is going to be the phase 1 report, which handles the baseline water quality, hydrology and water quality model. And then there's a phase 2 that goes through the BMP model and the optimization framework. Those documents, again, are going through peer review. They will be posted to this repository here once those become finalized in the next couple of weeks. In the meantime, the system is being launched. The user manuals and everything to help work through the workflow, the utilities, everything's working here. So we encourage folks to, you know, play around, become familiar, download the models, and do everything there. The documentation, the reports are just that. It's the full documentation and the citations and everything. So if you were to cite WMMS in the future, those would be the documents that you would cite. So we have a little over half an hour, and it's probably a good time to open it up to another round of Q&A. So TJ, I don't know if I'm sure you've received some new questions.
Yeah, I did receive some questions, and I want to echo what Steve said. I forgot to mention in the beginning, we wanted to increase transparency of this whole RIA process. That's why we are revealing this black box. We don't expect everybody to understand everything. You do need to hire experts, qualified experts to run these analysis, but if we at least introduce you to what they're doing, you have a better understanding of what needs to be done to do an RIA. I also want to say this is a regional program, regional calibration. If you want results that are watershed group specific, that is something that each group will have to do on their own. I want to mention that the model is only calibrated up to June 2019, and the MS4 permit requires you to update it up to the 2020 storm. So there's more calibration, validation that needs to be done for each group. So this is, it is a finished product, but it is not ready. You can't just run this off the shelf and expect to get your RAA results. There needs to be a lot of fine tuning, a lot of watershed scale, city scale type of input that needs to be put in to get your appropriate RAA results. So I'll go on with the questions. I'll start with the sustain questions. Is there a efficiency function for sustain, or is it always static for the efficiency of the BMPs?
That's a great question. And in sustain, we are using a process-based approach in that we're simulating the hydrology, the movement of the water, the infiltration, and so on. The key terms that we have are, there's a term that's for first order decay that's representing the time-based loss. That's just a function of how long the water stays in the BMP. So for like a wet pond or something like that, that has that kind of a mechanism, where time is the primary response driver for the treatment, that term is there. But in most cases, when there's a soil medium, there's filtration that's occurring, the model gives you the ability to specify either a percent removal for the water that flows through the output, or to just specify a capped effluent concentration for that outlet. So those are the terms. In the course of a storm, you're going to have some events that are completely contained and treated. So the performance during those smaller events is going to look just like the performance through the treated effluent underdrain outlet. In the case where you have a bigger event where there's some bypass, water mixes, or even bypasses the facility altogether, in those cases, the performance is going to look a lot like nothing. It's depending on the size of the storm. So that's what sustain provides in terms of the physical process-based response, is that spectrum of performance, because that's simulated as a function of the storm size.
Okay, and I have a couple of ramps questions. Estimated capture, does that also account for sewer diversion and treat and release projects? Maybe Dustin could answer that.
Yes. Yeah, so the ramps has the ability to handle diversions to sanitary sewers and treatment devices. And if some of you might remember this term that we use, it's called volume managed. And so it's actually, ramps will quantify both what was soaked into the ground and then what was treated and released. And so that both of those elements are captured.
Okay, and then more questions regarding ramps. What's the basis for the capture estimates in ramps? How is the runoff modeled? How is the diversion and BMP functioning modeled?
Ramps uses LSPC and sustain. So it's for each BMP type that's available in ramps, there's an assumption about the typical configuration or design of that BMP. And then so the user puts in the amount of area that's draining into the BMP, and then they also give some details on the BMP, and then ramps uses LSPC and sustain to get those estimates. Ramps itself uses a massive database of simulations that are pre-run to get those estimates when you're looking in ramps, which is a little bit different than the capture dashboard, which actually does the simulations real time on the cloud.
Okay, and a question regarding bacteria. Maybe we could spend some time going over the critical condition storms. Is how do you model bacteria? Is there a way to optimize volume or critical storm capture? Or with a group of BMPs when bacteria is the controlling pollutants?
I could keep talking.
John,
yeah.
You guys want to?
Why don't you click on, well, whoever's running, can you click on the documents, data, and downloads tab? And then you're there. And then in LSPC, just scroll down to the boundary conditions. Yeah, keep going. There we go. Yep. So many of the EWIMPs used what we called a bacteria storm. And the bacteria storm accounts for the allowable exceedance days that each watershed has. So those come from the TMDLs and the high flow suspension. So why don't you click on the PDF? You'd probably rather see that than the, there's a PDF in this file from the bacteria storm representation that shows how we've come up with bacteria storms in the past. There's certainly other ways to come up with bacteria storms, but these boundary conditions are provided so that users could do their own simulations of bacteria storms. It's a 24-hour storm based on the number of exceedance days. There we go. Yeah, and whether or not the high flow suspension is applicable to that modeling area. And so it turns the bacteria problem into a runoff management solution. I just need to manage the runoff from the first day that occurs after the exceedance days and after the high flow suspension. That next day, that's the size of the storm, and you need to be able to manage that storm in order to comply with the TMDLs. That's a conceptual model behind this approach. There's certainly other approaches to deal with bacteria storms, and we're not necessarily prescribing this approach, but we wanted to make that option available so that people could mimic those simulations that were performed in the original round of the EWIMPs.
Yeah, so I think that table that you guys just passed, the table below, that bacteria storm is highlighted in a dashed black line. Everything above that is an allowable exceedance day, and then that black dashed box, those would be the critical storm for that the first exceedance day, the largest storm.
For the 10-year period, and then the second highest one is the 90th percentile bacteria storm, and so that would be the one that you manage.
Yeah, so we are not modeling bacteria, but we're modeling the storm associated with bacteria. And if you guys go back to the website, I also want to point out that we have a similar storm for the 85th percentile. So if you just want to know what's my 85th percentile volume and you don't want to download 10 years of data and calculate the 85th percentile, what we've done is we've already made a pre-made 85th percentile storm for you. And also we have a average and 90th percentile critical water year as well. And so these are prefabricated storms that we've already made to help you with your RA analysis. Another question was regarding the second tier optimization. It says, I don't fully understand this question, but graph shows a constant acre feet per million. Shouldn't this graph show an increasing or decreasing benefit cost for each BMP? That was Alan's question. I don't know if, Alan, you want to elaborate on that. You can unmute yourself, Alan, if you want to ask.
I think we understand the question.
Okay.
Yeah, John, you want to address this one?
All right, sure. So, I mean, what we're seeing here in these graphs, the performance is over the entire simulation period. So it was for the critical year. Ryan ran this storm for water year 2010. And so this is the average performance over water year 2010 for all of the BMPs within that network, and also the major BMPs with 2 and 3 upstream of 1 in that network. And we're evaluating at the most downstream outlet of the watershed. So all those 12 jurissheds at the very most downstream outlet, this is the performance across that study area. And so what we're seeing in here, you will have an increasing percent reduction with the increasing size. The capacity is read as the stacks, and the cost is this curve. So the costs are increasing mainly as you add BMPs. That's just a direct relationship to that. The capacity is what changes. And as you toggle through this, you can look at what happens if I optimize for flow. I can look at the benefit towards nitrogen. And so the curve looks a little different for nitrogen. These are like the secondary benefits that I get if I look at lead. It's a slightly different shape. So what's changing here is the x-axis, right? Because we're changing the pollutant. So whereas I was getting a 22% for the same footprint of BMPs for lead, I get, if I look at zinc, almost 28% for that same slice.
Well,
and this is,
if you hold on that, I think to answer the question too, is that the regional BMP is flatlining because the capacity of that BMP is basically being met. And then once that regional, and that's a regional project, once that regional project's capacity is met, then it's adding another project on top. And so that's why that fuchsia, that purple isn't going up, is because that regional project capacity is maxed out basically. So, and then at that point it's building BMPs on top.
Okay, another question was regarding the rainfall. Will we be providing input files, weather files for the 2020 up to the 2020 storms to be uploaded? I know Ben Willitson asked that question. I'm gonna try, Ben. That's all I can say, because this paradigm contract is done after today, and it's up to me to update that weather file. And I do have like a spreadsheet tool to update the weather file. It's just I've never used it before. I'm gonna try my best to update the. I think a lot of people will be asking for it, so I'll try my best. But the water quality data, that's for each group to have on your own. We'll just try to provide the rainfall data. And then another question was, so I'm going to try to summarize this. We did a regional calibration, regional validation, and what if in my group, the monitoring data is different compared to the regional calibration, and it would result in a lower BMP need. And so I would respond to that saying that's why each group needs to calibrate on their own. That's why each group needs to look at their group by themselves, because we did a regional calibration, a regional validation, a regional model, but it's up to each group to really look into each group. Was this properly calibrated? Is this correct? Are all my BMPs in there? Are all these little idiosyncrasies that are not reflected in a regional calibration in there? And each group would need to adjust it to make sure that your monitoring data reflects your group modeling results. So that's what I would respond to that. Steve, if you want to add on to that as well.
Well, I think, we also provided a snapshot through comparison with all the data through 2019 for the SIMP data. And so, you can look there to see how the model's performing. But yes, I think it would be up to each group to further calibrate the model and meet any additional, calibration metrics for the region board's RA guidelines. I know we got it as far as we could through this regional calibration. And then, you can quickly look at those results in the comparisons to the SIMP data in the phase 1 report that'll be released in a couple of weeks to see how far you have to go for further calibration. Or if you need to.
Yeah. Any other questions? That's all the questions I've got during the past hour. Any other questions? You could just unmute yourself and ask if you'd like. No questions? Okay.
Well, one thing, if there are further questions, we put there's a new WMMS email. Maybe TJ, you're going to say that. I know one of Ivar's question was where do we download the models? So here is actually the old WMMS website now gets direct to the new WMMS platform that's going live today. But if you have any questions in the future, you can always email the county at this email address here that's specific to WMMS.
Yeah, and just a shorter, we made a short redirect. If you just do LACountyWMMS.com, it'll just redirect you to this portal.safecleanwaterla.org/WMMS.home. So I put that link on the chat, LACountyWMMS.com, and that should lead you directly to this page. You could go look through it right now, download the website, download the program, install it, play around with it, download all the GIS files. You guys can start playing around with it right now. I got one more question. Does WMS include the Port of Long Beach, the Port of LA and the Port of Long Beach?
Yes. Ryan, I don't know if you have the sub-watersheds. We could put that back on the up on the PowerPoint. So I believe it covers portions, if not all. And I know that in past work that we worked on for some of the RAAs, some of those boundaries should always be relooked at, particularly around the port areas. But I think it depends. Yeah, so you can see it here. Yeah, we can't zoom. I guess we could have done it on the viewer, but I guess the quick answer is yes and no. It includes the subwatersheds that were available and had been used in the past for the county. Now, when we did specific RAAs in the past, particularly for the city of Long Beach, there were some additional modifications and considerations to represent those areas where we were literally looking at aerial photography to make sure that those subwatershed boundaries were correct out in the port areas. So there can always be some modifications.
Hold on, some people are saying the website is not working. I think it's working.
TJ, I've noticed that sometimes a backslash or a forward slash rather gets added sometimes to URL, so it should be free of a forward slash, that URL. And so if someone adds that to it, it will not take you to the web page. It may be the issue that those people are experiencing.
Yeah, I have it working fine too.
Yeah, and I just tried it with the LA County WMS.com and it worked fine. The redirect worked fine. Oh, I got a couple people saying they're getting a blank screen. So I don't know. It's working for me. It seems like it's working for Paradigm. Anyone else try it and got it to work? I got at least 3 people telling me they got a blank screen, but
So there should be no forward slash at the end of the
show them the link again,
link.
Ryan.
Yep, that's the link. Mm-hmm.
And then if you could put on that PowerPoint, LACountyWMS.com as well.
Oh yeah. LA County.
www.LACountyWMS.com. It's working for me. Need to have the HTTPS. That's what Joe is saying. Okay, they said the last
Okay,
link worked.
good.
Okay, so it seems like it's working. Make sure to include the HTTPS in the link. You can't do it with just portal.savecleanwater. Okay. Okay, so that's important to know. Add the HTTPS or just use lacounty.wms.com. All right, well, any other questions? If you have further questions, you can send it to me, wms@pw.lacounty.gov. And we'll try to answer your questions. This PowerPoint and the video will be hosted on the website. And like Steve said, hopefully by next week, all the documentation regarding the calibration and the background, the costs, and all that will be on the webpage. We're hoping to get that up maybe by the end of next week. So I think that's it. Well, thank you all for coming. I know it was a lot of information, and thank you for hanging in there, all 127 of you. Hopefully, if you go through all the documentation, everything, it'll make sense. Again, we're not trying to make modelers out of you overnight, but hopefully everyone is starting to understand what goes in the process and to have a successful RAA in 1 year from today. So hopefully, cross your fingers, everyone has a good RAA. If you have any questions, please let me know.